Recording. All right, it's recording and it's recording the right screen. All right, so I can proceed today's class in several directions. We can go over the solution of the swap homework assignment. We can proceed to talk about more sample programs related to structures. So, anything you guys want me to talk about except for the solution of homework assignments that are still yet to be submitted. So what do you guys want to do? Yep, the swap function. Okay, so we'll start with that. All right. So I do want to reintroduce, the resource that is available to you, which is on ChatGPT. So I sent you guys a link to the TTP ASM tutor, and I tested it this morning, and I was surprised to find out that it is actually more capable than I thought it was. Okay, so we'll get to that when we get to that point. Okay, all right. So we'll start with the implementation of the swap function, the actual homework assignment. And as usual, I will display the C code on the left-hand side and the TTP ASM or just the assembly code on the right-hand side, like so. The main function is already done, so that means there's nothing for you to do regarding the main function. It's already done here. Well, I said nothing to be done, but you might want to still kind of look through that and see, how local variables x and y are allocated and which location has which one. Okay, so I'm going to do one thing that I haven't done before, okay, to test out, the capability of ChatGPT. Okay, so we'll go to here. And what I'm going to do is to give it exactly the function or the code that is already written in main, and ask ChatGPT to show me what should be on the stack and explain what items are on the stack by the time we get to the entry point of the swap function. Okay, because I think that part is actually important too, because otherwise how would you know where to find the parameters, right? And where is the return address? So I think that part is actually important. So what I'll do is I am going to go to a separate prompt here and copy the code from swap.ttp ASM as it is given to you. So this one has no additional code that I have written so far. So I will ask your ChatGPT, the tutor thing, a particular question. I will ask it, can you show me what the stack should look like at the entry point of the swap function and explain item what each item is on the stack. Okay, the following is the code. Okay, and that's just how you can specify a block of code. It's triple backtick. Okay, so I'm just gonna let ChatGPT cook on this one for a little bit while I go back here and try to implement just the swap function. So the swap function has two parameters, pointer one, pointer two. It has a local variable t, and we need to do a bunch of operations with those. But without understanding, how the stack should be set up, there's no way, the program can be written. So the first thing that we really need to do is to find out how memory is going to be laid out. Um, so let's go ahead and start with that. So the way I want to do this is to specify what the frame should look like. So the frame is referring to all the items on the stack that are necessary for this invocation of swap to function. So that would include all the local variables, if any, the return address that must be there. So the return address is not optional, and the parameters, if any. In this case, we have all three categories. We have one local variable t, with one return address, and then we have pointer one, pointer two as parameters. So the question now is, Where are those things on the stack? Pointer 2 is pushed first by the caller, and that's based on the caller-callee agreement, so it has the highest address within that portion of the memory on the stack. Pointer 1 is pushed second, so it has the lower location, okay, it's 1 byte below pointer 2, and then the caller will proceed to push the return address. So the return address is going to be at the next location or lower than pointer 1, and so at the entry point of swap, that's what the stack would look like. And the stack pointer is pointing to the last thing that we push or allocate on the stack. So at this point, the stack pointer points to the return address. Local variable t does not exist yet. Okay, it has not been allocated yet. So that means what we need to do is to find out, okay, how many bytes do we need to allocate for all the local variables and blah, blah, blah. So the way we do that is we look at the C function, and since it only has one and only one local variable, it is both the first and the last local variable. So the convention that I do is the first local variable would be at the bottom of the entire frame. So it has an offset of 0 from the base of the entire frame. So these are just labels to help me access individual items. And an LVS, which stands for local variable size, is going to be the offset to the last local variable. But it's the same because we only have one single local variable in this case, plus the size of the local variable. And because we have to specify expressions in postfix notation, it is 1 plus. And then after that, we also want to have the offset to go to pointer 1, and that would be swap underscore LVS 1 plus. The reason why that is the case is because at the location of swap LVS as an offset from the base of the frame, we'll find the return address. The return address is right there, and we have to skip past the return address to get to the first parameter. And then the second parameter, pointer 1, is going to be right after the first parameter. So the offset to the first parameter plus the size of the first parameter would be the offset to find the second parameter. So this part is important because that helps me, one, calculate how many bytes I need to allocate for all the local variable, in this case just one. It also helps me to create all the labels to access the parameters at the same time, because otherwise I would have to remember just 3 and 4, but then I have to remember which one is which. Using the symbolic names is a whole lot better. Okay, so I think ChatGPT is done baking on the other side. So now ChatGPT specifies what should be on the stack. So from the stack pointer, okay, the stack pointer should be pointing to the return address right at this point, and then we can find parameter p1, and then we can find parameter p2. And is that because I used the wrong? Oh, I didn't give it the C code. So it's working out. It's working out of this without the C code, which is also kind of impressive. Okay, because it's just working out, everything, by looking at the context, and it's explaining why py is at a higher location, which is at the offset of 2 from where the stack pointer points to. And then logical validation. Okay, it's also just double checking its own calculation. So now we also want to define the labels of where to find stuff. But this is not going to be sufficient because it's not taking into consideration that we have a local variable. So now we can go back to the assembly code here, because I forgot to give ChatGPT the C code. So that's all it can work out because it doesn't know there's a local variable here. So, but we do, okay? So that means the frame, when it is all set up, is going to be more like this. Okay, we have these items here, but then we also have local variable t over here, and after local variable t is allocated, then the stack pointer should point over there. And this, where local variable t is the base of this entire frame. Do we have any questions about the concept of a frame and why the various items are at those particular offsets from the frame. So this part is okay, all right? The label definitions alone do not move the stack pointer, okay? In other words, from line 36 to line 39, those label definitions do not do a single thing to the actual register D. So that means, in order to make that adjustment, we have to LDI, into whatever register you want to use, A, B, or C would be fine. I'll use register A here, swap LVS, and subtract that much from the stack pointer. And just this is just my own programming style. I would also end the code with undoing the same thing, and I might as well just also finish just the return code here, which is LDBD increment D and then JMPB. So with these two instructions in place, then the stack would actually look like this, because it was like this before. By subtracting one from the stack pointer, it would look like this. So are we okay so far with how the frame itself is set up? Okay, very good. And if I were to copy and paste the swap function itself into ChatGPT and ask about how the frame would look like, it would actually give you this picture as well. So I just want to illustrate it because just in case you want to do something similar with your other two homework assignment, you now know that there's a tool that can help you visualize what should be in a frame. So I'm going to do just that. So this time I'm presenting the C code into the conversation here, and I'll just mention that the above TTP ASM code is a partial implementation of the following C code, and then I'll give it the actual C code here, and then I'll ask it, can you show me the frame and items in the frame, items and its items, okay, and its items for function swap. So now it has a much better context because I'm also providing the C code. So we'll let it bake a little bit here. Okay, we'll go back to my verbal explanation and then let ChatGPT kind of do its own calculation stuff. Okay, so now our focus is going to be on line 4 of the entire program. Now this would be a good point to stop and go like, okay, how do we know what we are supposed to be seeing on the stack at this point, and how do I double check that it is working the way it's supposed to? So what you can do is to put a halt instruction here. In other words, I'm not done with the program, okay? In fact, I haven't even, quote unquote, gotten started with the actual code, which is line 4, 5, and 6 of the C code. But you can put a halt instruction here just so that you understand what is supposed to be on the stack, okay? So at this point, I'm going to go back to ChatGPT and just kind of look at how it has baked, the stuff I have told it. And you can see how in this picture, it is resembling exactly what we had in the comment of the assembly code. Okay. In other words, what I did was I gave ChatGPT the same documents that you have, the opcode table, the caller quality agreement, and a whole bunch of other stuff that that are linked from the Canvas shell, and ChatGPT was able to work with all of those things and kind of go like, okay, this is my understanding of how the stack should look like, and these are the frame items, and it will even tell you which item exists, because of whom. Okay, pointer one, pointer two were pushed by the caller. The return address was also pushed by the caller, and then local variable t is allocated or supposed to be allocated by the callee. Um, so do we have any questions about this? Because I think this is actually a fairly useful tool, because you can interact with it. Um, as opposed to, I mean, you can come to my office hour and ask me questions as well, but I only have 1 hour of office hour, and even if you can find me on campus, during my other time, it is still limited. This is a resource that you can have, access to, basically 24/7. Okay, and I instructed this particular chat GPT or custom GPT not to give you a direct solution. So that means it's going to give you some clues. It will explain things, but it's not going to give you just all the code that you need. So you don't have to worry about. But I don't want to see the code. I just want to understand how to get it working. So this is a potentially useful resource. Okay. So now we go back to to the implementation, and this is our first line, which is the first thing we need to do is to access my typical convention is to work on the right hand side first for most cases. So in this case, I need to get to the right hand side first, which is the value that is pointed to by pointer one. But pointer one itself is a parameter, which means it lives in the frame, which also means in order to get to the value of pointer one, I need to get the address of pointer one first. But to get to the address of pointer one, all I have is the offset from the base of the frame. So I need to add that offset to the actual address of the entire frame, but the stack pointer is pointing to the base of the entire frame. So that means I can add the stack pointer to the offset in order to get to the address of pointer one. After that, I would dereference it once to get to the value of pointer one. And then after that, I would dereference it one more time to get to what pointer one is pointing to. That becomes the right-hand side of line 4 of the C code. Okay, so let me just pause a little bit here because what I said, that was a chain of reasoning. In other words, I'm working out this is what I really need, but what does it need in order to get it done? Okay, I need to get to the content pointed to by pointer one. Well, I think I need to get to pointer one first, but how do I get to the value of pointer one? You can only get to the value of pointer one because pointer one is in a memory location. You have to get to the address of pointer one first. But how do I get to the address of pointer one? You look at all the things that are available to you. We have the offset of pointer one from the base of the frame. Well, that's good, but that means it's also not the direct answer. We need to add the address of the frame to the offset from the base of the frame to pointer one to get to the address of pointer one. So I'm doing all the reasoning backwards, but it is still going to be helpful. Okay, so we can now say LDI, you can use any register you want, swap underscore pointer one, which is the offset from the base, from the frame base to pointer one itself. In other words, I have two, okay, because it's supposed to be 2 bytes away from the base of the frame. So this is basically essentially just two. I put two into register A, and then I add AD. So now whatever D is not actually important, okay? As long as the caller gets the job done correctly, I now have the address of pointer one. And if I do one dereference, I get to the value of pointer one, but the value of pointer one is the address of what I need on the right-hand side of line 4 of the C code. So that means I need one more dereference in order to get to the entire right-hand side. Okay, so I'm going to stop here and I go like, okay, that's a whole long chain of reasoning. Am I actually doing it correctly? So the way you check whether you're doing it correctly is to look at the C code and ask, what should be the value of the expression of the referencing pointer one on line 4? So now you have to think about, okay, what did I pass to pointer one in the C code? In the C code, we are passing the address of X as pointer one in as a parameter of swap. So that means pointer one is the address of local variable X of main, which was initialized to a 3. So that means at this point, I should end up with a value of 3 in register A. Is that okay? So knowing what you should be expecting, is very important because otherwise there's no way to debug because the debugging process means you're comparing what the program is supposed to do against what it is actually doing. So now, how do we know whether the program is doing this correctly or not? There are two ways to do it. We used to only have one way to do this. Now we have two. Okay, so I'll show you the typical way first, okay, which is consistent with what we usually do, which is using River Spider and actually run this code through the simulator. So we'll go ahead and run swap.ttp-asm, which is only partially done. We have only gotten the right-hand side of line 4 of the C code done, but we should see register A being 3 at the very end of the trace. So now we go back to the assembler. Okay, it needs to be refreshed. And then we go to the end of the trace and we see register A being 3. All right, so that's good. Okay, we have a confirmation of one, we know how the frame is organized. We know how to get to parameter PTR1 pointer 1, and we know how to dereference pointer 1 as well. So this is a big deal because that means, oh, I think I have all the pieces that I need to finish the entire program. It's just a matter of, oh, are we loading or versus are we storing? Because if you're changing, then you're storing. If you're reading, you're loading. So that's one way to do it. Just this morning, I found out that ChatGPT can also do the simulation. That was surprising to me because I never told ChatGPT specific information about emulating the processor, but it can actually do it. So let me just go ahead and show you what it can do. Um, so I'm gonna have to copy the whole program again, but this time it is the TTP implementation. So TTP ASM, and then we go back to ChatGPT, and this time I will say, I have a partial implementation of the program. Can you simulate the execution and see if register A has a value of 3 um, when the program halts? Please also help explain what is in each register and what is on the stack as the program executes. Okay, I know this is really kind of rather long explanation, but that's basically what you need to do when you are, kind of talking to a chat GPT thing. Okay, so you give it the entire program. Okay, I just copy and paste the whole thing and the 3 quotes here, and then press the enter key. It's going to take a while. Okay, so once again, we're going to go back to the C code and continue with my manual explanation when ChatGPT is baking, the simulation. Okay, so we already have a confirmation because I ran this through River Spider, but I'm just saying that in addition to River Spider, especially for those of you who, for whatever reason, have not or do not want to set up your River Spider, now you have a second mechanism to kind of quote unquote run the program through. It does require a lot of resources with ChatGPT, so you might need to actually pay for the $20 per month fee in order to have this kind of access. All right, so now what do? We want to use the right-hand side to change the left-hand side. So the left-hand side is referring to t, which is a local variable. So once again, we are asking the question, how do we store something to the memory location corresponding to local variable t? I think we need the address first. Okay, so so the answer to that question is we need to get to the address of local variable t in this frame. How do we get to the address? Well, we have the offset. Okay, so line 36 basically says um, local variable t is right at the base of the entire frame. Or you can also say has an offset of 0 from the base of the entire frame. So we go like, okay, so if I add that offset of 0 to the frame, the base of the entire frame, I would have the address of t. So now the question is, how do I get to the address of the base of the frame? Well, the stack pointer is still pointing there. Okay, so the stack pointer is still pointing to the base of the entire frame. So that means, okay, so if I do LDIB with swap underscore t, which is actually just 0 in this case, but I just want to write my code to be not brittle. So this way, if I want to introduce additional local variables, it wouldn't impact this code at all. Okay, so now we have the address of local variable t in register B, and that's exactly where I need to store the value of the right-hand side. So this should accomplish what we want to do. All right. So now we did I put this in? Oh, no, this is the correct location. So now I go back to ChatGPT and see whether it confirms what we thought would happen earlier. It's doing some funky stuff actually. Well, okay, it's not funky. It is just looking at FF as -1 and FE as -2. Um, so I'm just scrolling all the way through, and it confirms that at that point, register A should have a value of 3 with a bunch of really verbose, long explanation along the way. Are we good so far? Okay. So this is an ability of ChatGPT that I was not even aware of until this morning when I decided to go like, hey, I already finished the implementation with the Tuesday Thursday class. Let me see if ChatGPT can actually emulate the execution of the entire program and confirm the correctness of the program, and it was able to do that. So that means you can potentially use this as a way to debug your program. Okay, potentially. I haven't really fully tested out the ability for of a ChatGPT to reason out, whether you have a problem or you have a, whether the code is incorrect or not. It also gives you, certain things like, retrieve return address. This is not correct. There's no such addressing mode in TTP. Um, and it's also missing the increment of but that's way past the point that I needed to finish. It's actually doing it's doing way more than what I asked it to do, because all I'd ask was, I just need to confirm there is a 3 at the end of the execution of the code. I did not ask it to finish writing the entire program. It actually attempted to write the entire program for me. All right, so getting back to the manual side of implementing this program. So right now, if I look at the stack setup, okay, in other words, let me go to the share folder, and this is the correct one. I will create a new spreadsheet for this class. Okay, this is the Monday, Wednesday class, and it has today's date as the name of the spreadsheet. So what I want to do is to show you how you can figure out what should be on the stack at this point, just up to the instruction that we have talked about. All right, so we are looking at locations 255, and this is going to be this location -1, and a bunch of stuff like that. And then we have the um, hexadecimal representation of the same addresses. So we have FF all the way down. We don't need that many locations, but I'm just putting it all there. All right. So this location is supposed to be Y of main, and that's actually documented in the assembly code of main. This is supposed to be X of main. I believe this one is initialized to a value of 7. This is initialized to a value of 3. This is going to be parameter PTR2. Okay, so PTR2 pointer 2 of swap is supposed to be here. And I passed the address of Y as pointer 2. So that means the value here should be FF. I passed, this is supposed to be pointer 1 of swap, and I passed the address of X of main as pointer 2 to swap, so this should be FE. And then this location is the return address to main, which I don't know exactly what it is. It's not super important. This location is supposed to be T or local variable T of swap. So that means if you focus on these 4 locations, they become the frame of swap. So I'm going to highlight it, in a particular color. Okay, so where's my coloring tool? Right there. Okay, so we'll color these 4 bytes, because it is the frame of swap. The stack pointer, once everything is done, the stack pointer should be pointing here, and we're expecting the 03 to be stored over here. So that's what the program should have done up to this point. I go back to my assembly code, okay, because I needed to, basically stop working any further, because that's all we have at this point. So we put the swap instruction right here. In other words, I think that we have just completed the implementation of line 4 of the C code, and I want to confirm it. Because if line 4 is not implemented correctly, then I probably should not continue with the rest of the program because it might reflect that I do not have a good understanding of how to do things, or I made a clerical mistake and I might end up, kind of messing up something else. So the rest of the code is not going to run anyway. So I put a halt instruction here, and then I do the same thing, in, um, run it through Reefer Spider. Okay. So this is the part where things get a little bit more difficult to read. Okay, it's all done already. Because now you have to focus on column C and find out, how do we put things into column C. So the column C says location FE should be a 0, 3. Is it consistent with what I thought it should be? Yep, FE should have a value of 0, 3. And then it says the next update is location FF. It should have a value of 0, 7. And now we go like, okay, is that actually consistent with what we thought it should? Yep. Okay, here's the 0, 7. And then we go back and go to the next update, which is location FD is supposed to be FF. We go to our prediction, location FD is supposed to have a value of FF because that's the address of local variable Y of main. Yep, checked. And then we go to the next location, which is FC is supposed to get FE. We go back here and go like, yep, that is consistent. And then we have the return address stored at location FB. So we go back here and then we just check it. It is 17. Well, is 17 the actual return address? It's good to double check it. So the only way to double check this one is to go to the assemble view, go to location 17, which is in hexadecimal, and you ask, is this the instruction immediately following the JMPI instruction? Yep, here's the JMPI instruction to go to swap. This is just a label definition. So the immediately following instruction is indeed at location 17. So 17 is the correct return address back to me. Okay, so far so good. Then we move on, okay, because we said that eventually we should see location FA storing a value of 0, 3. And that's what the trace said, but that's also what we see at this point. Now, there are a few other things you should probably check too. Is register D really FA? In other words, is the stack pointer pointing to location FA? You can check that too, because you just have to look up the last update to register D, and it was indeed FA. So this is how I can gradually check my steps one by one, or just a few lines of assembly code at a time, in order to double check that my implementation is correct. And along the way, in every single step, I'm also reinforcing, okay, do I know how to get to items on the frame? Do I know what a frame is? Do I know where the stack pointer is pointing to? Do I know how to allocate and deallocate the local variables? So I'm confirming all of those things, along this way. Do we have any questions at this point about, the concepts that are involved, about the process that I have been demonstrating, or about the tools that you can use to verify the execution of the program up to this point? We all good? Okay, excellent. So that means gives me a lot of confidence because the right hand side of line 5 is pretty much the same as the right hand side of line 4, except we're dealing with pointer 2 instead of pointer 1. So that means, I can probably just use the template that we had earlier and go like, okay, this time it's just, pointer two, but, the way we calculate the address, the way we get to the value, and the way we get to what pointer two points to would be exactly the same. The only difference is what do we do with the left-hand side? So the left-hand side of line 5 says we need to store to the location that is pointed to by pointer 1. Okay, so that means I have to calculate the address first. The address of where I need to store is pointer 1 itself. So that means I need to get to the value of pointer one. To get to the value of pointer one, I need to get to the address of pointer one. To get to the address of pointer one, I need the offset from the base of the frame to pointer one, and also the actual address of the base of the frame, which is still the stack pointer. So that means you're reversing what I just said. I just need to get to the offset first, okay? The offset to pointer one, get to the address of pointer one, get to the value of pointer one, and then we get to the content of pointer one. But this time, I'm not going to do another BB because that will just read whatever is currently pointed to by pointer one. But my intention is not to read it. My intention is to overwrite it. So that means we have to change it to a store instruction. So instead, we are storing to wherever register B is pointing to, and store to it the value of the right hand side, which is already computed earlier in register A. So that's what I think would implement line 5 of the C code. But I'm not going to make any assumptions and go like, okay, let's just assume this is working and we'll continue. I'm going to test it again. But this time when I test it, I would go to the map here, okay, the map that I showed you a little bit earlier, and ask, okay, what is supposed to be changed this time? This time I'm taking whatever pointer 2 is pointing to, which is the 7, and then use it to override whatever pointer 1 is pointing to. Pointer 1 is pointing to location FE, so that means I'm expecting this location FE to be changed from a 07 to a 03. Oh, excuse me, from a 03 to a 07. That's it. Okay, so we'll go ahead and type that in. So from a 03 to a 07, and okay, my intention was to use the strike through thing, which is Alt Shift 5. Okay, so this is basically showing that it should change from 03 to 07, which is and we are referring to location FE. All right, so with that prediction, knowing that okay, I think this is what should happen, I can now go back to my code, go to Logisim again. Go to River Spider, which uses Logisim to simulate the execution of the program. Get back to the assembler, go back to the analysis tab, and said, did I make that change? Nope, because I forgot to save the program first. That's typical of me. But before I do anything like that, I'll do a Control G. This is specific to VI because it showed me that the file was modified and I haven't saved it yet. Okay, so this really typical of me, forgetting to save the file before testing it. So let's do it again. All right. So now we should see more code to be run. Yes. Okay. So and the last update is at location FE. It is changed to a 07. Is that according to my prediction? The answer is yes. So that means up to this point, I am testing my program, every step along the way, every 8 lines or so. You can also do it, every 4 lines or so. Okay, just do it in smaller steps, and now I can finish up the entire program, which is getting whatever whatever local variable t has, and then storing that to whatever PTR2 is pointing to. Well, that should be fairly easy now because I have already confirmed that I know how to read what a pointer is pointing to. I know how to overwrite what a pointer is pointing to. So the only new thing here is, do I know how to read the value of a local variable? I think if I can store to it, I know how to read it. So LDIB swap. Okay, let's use A again. So I'm using A consistently for the right-hand side and B consistently for the left-hand side. So LDIA with a swap T. That's the offset. This is now the address, but I need the value because I don't see an ampersand here. So that means I need to load AA. So now A is the value of local variable T, and I need to store that to PTR2, but I already know how to store to PTR1, so storing to PTR2 is repeating kind of the same template, but this time I just have to change the pointer from pointer 1 to pointer 2. So do that, get the value of the pointer itself, and then store to where the pointer is pointing to. And register A already has the right hand side. So now I should finish the entire operation. In the prediction, over here, that means that whatever was here, which is a 07, should now become a 03. And I'm going to strike through the 07 to indicate that is the update. Okay, we're changing it from 07 to 03. So Alt Shift 5 again. All right. So now we can go back and make sure I save the code first and then run it. So there we go. All right. So then we go back to, what was it? Oh, right, the assembler. And that should finish up with an update of location FF should be changed to 03 from whatever it had before. And that's exactly how we predicted it. So at this point, the body of swap is all done. But I'm not really done yet because I need to make sure that it returns correctly, the local variable gets deallocated and all that stuff. So I would go back to the source code over here and just remove the halt instruction because I already put in this code earlier to deallocate the local variables and also to perform the actual return to main. So that part is already done. I just need to test whether that's working or not. So save the code and just run it one more time through Logisim and see if we complete the execution of the program entirely correctly. All right, so now we go back here. Okay, this is where we left off last time, and then we just continue to take a look at the program. When the program ends, register D, the stack pointer is back to location 00, so the stack is balanced, and we are ending up at a halt instruction in main, so that is the correct halt instruction. So that is kind of how I would confirm that the program worked correctly. All right, so it's time for me to kind of shut up and at least pause and see if you guys have any questions. Your questions can be regarding the concepts that are involved, like how do we pass parameters or pass arguments? How do we access things in the frame? What things are in the frame? Why are they in the order that we specified? And once we try to write the code, how do we get to the value of something, okay, like a parameter or a local variable? How do we dereference a pointer? So you can ask those questions. You can also ask the question of how to use the tool, okay, All right, since you guys don't have any questions, I'm going to ask ChatGPT a question, okay? So I will switch back to this tab here. This will take a while, but I'm going to ask the question. So I am going to, right. So I have to give it the C code. Okay. It already has the C code, so we'll see whether it remembers that. But I'll give it the finished assembly code. And I go to ChatGPT and I mention here, I think I have finished the implementation of the C code. The following is the TTP ASM code. Can you help me analyze and see if the code is correct? If it is incorrect, oops, if it is, if I cannot see it because of Grammarly, if it is incorrect, please explain to me why. Okay, there we go. So here's the actual finished TTP ASM code. Paste the whole thing in. Up, I forgot to close it with three backticks. I think it is still okay. ChatGPT is actually pretty good with that. So we'll go ahead and just let it bake, okay? Just like those infomercial. We stick something into the oven and then we just kind of walk away and continue with the next topic. All right. Do we have any questions about the swap function? Okay. What about the other two homework assignments? Do we have any questions about those? One is about recursion, and then the other one is about structures. All right, so we're going to take a quick look at the recursion one first. Okay, even though you guys do not seem to have any questions, I'm going to go over it a little bit. So with a recursive call, okay, there are two key pieces that you need. One is the nested function call that you need. The second one is the Johnny, Ryan, and 12 sample program. One would illustrate what do you do when you need to add the return values of two function calls. Because when you perform a function call, according to the caller-callee agreement, all registers may be modified by the function. So that means you cannot use a register to save the return value of an earlier invocation of a function, because the second invocation is going to destroy all registers. Okay. So now the question is, then what do we do? Because we're going to lose the return value when we call the function again, even though it's a recursive call. So the correct solution is when we talked about the Johnny, Ryan, and 12 program, we used the trick of pushing the return value of the first call on the stack first. Okay, so that's the relevance of why that particular sample program is useful. Then what about the nested function call? Did we talk about the nested function call where I give you a function and it call itself as parameters? I think it's add. You did. So that one is also useful because when we push an argument on the stack pointer is no longer pointing at the base of the frame. The base of the frame is always referring to the lowest location of the local variables, or the return address in the absence of local variables. That is always the address of the frame of a base, the base of a frame. But when you push arguments on the stack, you're moving the stack pointer so that instead of pointing to the base of the frame, it is now pointing to locations, potentially multiple locations below the base of the frame. So that means all the offsets to access items on the frame, they're now off by 1 byte, 2 bytes, depending on how many things you have already pushed on the stack. So you have to adjust for that. That is why the second program, which is the nested call to add, is going to be useful. So you have to combine those two concepts to get the recursive function call thing to work. Is that explaining everything? Okay, I'll let you guys digest that a little bit, and then I just want to go to ChatGPT, and the conclusion is the implementation appears correct. It adheres to the TTP stack convention, correctly swap the values of X and Y, and ensure that the stack is balanced after the function executes. And it actually go through the whole analysis thing. Yep, that is kind of I was impressed this morning because I just decided I'll give it a try, see what it can do, and it was able to do it. What I asked it was to simulate the execution of the program, so everything was step by step. I didn't ask it this time. This time I just asked it, is this a correct implementation? But when I asked it ask it to simulate the execution, it was actually able to go step by step and showed that the values of local variables X and Y of main were indeed exchanged. So it was able to understand the C code as well as the assembly code, as well as to simulate the execution of the assembly code and understand the end result is consistent with what the C code should have done. So use it as a tool, okay? Because it really is quite good, okay? Understanding basic programming concepts. If you ask it to generate code, it is not quite as good, okay, because it will give you instructions or addressing modes that do not exist with TTP ASM. So in that direction, it doesn't help too much. But in the opposite direction, which is just asking it for ideas and concepts and how to do certain things, like very small steps, it is actually quite good at doing that. All right. So we still have what uh, half an hour, okay, of class time. So how can I answer your questions? Well, perhaps we can start with the final exam from the previous semester. Okay, so I will just kind of go there. And I just sent the announcement this morning. So if you don't have time to check it yet, that's perfectly okay. I'm not expecting people to check the email like every minute. Okay, so we'll take a look at the um, exam from the spring semester. So the thing about this one is, the instructions are going to be pretty much the same. Okay, I will give you the C implementation, which is on a separate page. So this is the actual C implementation of the program. And you can see that it has kind of the same stuff that you are dealing with right now. It has a structure definition. Inside the structure, there's a member that is a pointer to the same kind of structure. And then we have a function. Okay, in this case, the function um, has a pointer to a struct R, and it has a second parameter which is remaining. And it is also recursive. Okay, so there's a recursive call to itself. Okay, it has a local variable, but this time the local variable is not a pointer. This is an actual structure. Okay, and then we define, array size to be 3, and this is main, blah blah blah, and so on. So this is the C code. The first thing you probably want to do is because the C code is correct, okay? By definition, the C code is correct. Your job is not to fix the C code. There's nothing to fix in the C code. But you do have to understand what it does, okay? So that's the first thing you need to do is to understand what does the C code do? Well, in outside of the exam, you can use online GDB. Okay, you can just kind of test run it, put breakpoints in it, single step through the whole thing, and understand how the C code works. But your actual job is to look at the assembly code and try to fix the assembly code because the assembly code is going to contain a bunch of errors. So your job is to figure out what's wrong with the assembly code implementation. Now, because I'm giving you this way ahead of time, by the way, this is not your final exam. Okay, this is just a sample from the previous semester. Okay, but you have plenty of time. So that means not under the pressure of time. Now you can go like, okay, I'm gonna take my time and I'll try to develop a strategy of how to deal with final exams like this. Okay, so I would focus on strategizing, okay, in addition to understanding the concepts and being able to apply the concepts. So what have we talked about up to this point that is related to TTP ASM programming? We start with the basics, okay, the opcode table. What instructions are in fact available and what are the operands that are expected for each instruction? For instance, add A1, okay, I'll put it on the whiteboard here. Add A1 does not exist because both operands of add must specify registers. Okay, so there are little things like that. Okay, and when you use load, you cannot just say load AB because that is syntactically wrong. Whatever is the reference needs to be parenthesized. So in the case of a load, this one is parenthesized because we are reading from where P points to in order to update register A. So that means the opcode table is going to be the starting point of what you need in order to ace the final exam. And then what did we talk about after that? We talked about the stack. So the convention that we use in this class is the stack is what we call a downward growing stack, which means when you push more items, when you store more items onto the stack pointer decrements. Okay, it decreases as we push more items on the stack. Now, are there upward growing stacks? Yes. Okay, so that means we have to make an effort to remember that the stack pointer decrements as we push items on the stack. The other thing that I never really mentioned because I didn't know it was a point of confusion is the stack pointer always points to the last item that you push on the stack. Okay. Apparently, there are stack pointers that point to the next available location instead of the last item that was pushed, so it's off by just one. Okay. But in this class, the convention is the stack pointer always points to the last item that we either push or we allocate. Okay. So those are all very important pieces of information. And then after we talked about stack, then we go into the whole caller callee agreement thing. In other words, the only way for the caller and the callee to communicate with each other is to go through the caller callee agreements. So we start with, oh, if there are arguments in a function call, the arguments are pushed backwards. What does that mean? It means the last argument is pushed first, and which also means the first argument is pushed last. But based on the downward growing stack concept, it also means the last argument sits at the highest location, the first argument sits at the lowest location. After all the arguments are pushed, then we push the return address, which means the return address is lower than the first argument in the function call. And that's the obligation of the caller in the in the first part of a call. Then we do a JMPI to the function being called. So at the entry point of the function being called, we have the return address and all the arguments already on the stack. But if the function needs local variables, then the function itself is responsible to allocate for its own local variables. So that allocation of local variables is what finishes the construction of the entire call frame. Okay, and then at the end of the allocation, the stack pointer would point to the base of the entire call frame. And it's based on that assumption that I do all the calculations of the offsets to items on the stack. But if you allocate something, you have to remember to deallocate. So it is up to the function to deallocate its own local variables. And then after that, then the stack pointer should point back to the return address. And then at which point it is the responsibility of the callee to pop the return address, which means it is not only reading to find out what is the return address, but it would also deallocate the location that was used to store the return address from the stack, and hence the increment D in the 3-byte sequence to return to the caller. And then we return to the caller. If the caller pushed arguments in order to make the function call, then the caller is responsible to deallocate the space on the stack that was used by the arguments. And then if the callee has a scalar type return value, that is returned through register A. So that's pretty much the caller callee agreement in a nutshell. Are we doing okay so far with that? I'm just quickly recapping everything that is important for the final exam. Okay. And then we talked about structures. Okay, with structures, the way a structure is represented in assembly code is by a bunch of label definitions. Each label is telling us the number of bytes from the base of a structure or the first byte of an entire structure to the member that we need to access. So that's what those labels are for. We also need to calculate the size of a structure because in certain cases, we need that either for allocation or for incrementing pointers. All right. And then we also spend some time to talk about quote unquote compiling, which is basically looking at a while loop and understand, okay, how do we convert a C while loop into assembly code? How do we look at a conditional statement in C code and convert it into assembly code? So there's a very structured way to do it. It is all in the compiling, module. So do we have any questions about all of these things that we have talked about? it is a lot of material. Okay, there's no way I can say this is not a lot of material, but the ordering of the material in which they were introduced, they are, to me it is logical. Okay, to me it's logical to introduce the material in that particular fashion. What you're doing with the programs, both the next homework assignment, which is the Fibonacci number, and also the one that involved the structure, even the attempt to write those particular program is a way of studying. Even in the end, if your program does not work, you are still it is still time well spent, because in the process of writing that code and going like, oh, it's not working. Why is it not working? You're trying to debug it. Those attempts to write the code, to debug the code, to try to follow through the execution of the code to find out what is happening, that is all studying. Okay, so studying for this class is not about reading the modules over and over again, or watching the videos over and over again. It is about doing things, make mistakes, and then go back and find out what mistakes you have made. Because every time the program doesn't work, it can be one of two reasons. One, you make a clerical mistake, okay, it's a simple typo, okay, or it can be a conceptual misunderstanding of something. But either way, the exercise of going through the code using River Spider or ChatGPT, to try to figure out where the discrepancy is, that is studying. Okay, if I just give you the code that works and you just have to kind of piece it together or make some minor changes in the pattern and stuff like that, that is not studying. That doesn't really help, because all most people would do is to memorize the sequences. They remember the template without asking why or what it does. Okay, so that's kind of my spiel of how to get ready for the final exam. So now that you know there's an agreement, the caller-callee agreement, and there are structures to translate, control structure into assembly code. Now the question that I want to pose to you, okay, and you need to answer that question, because I'm not going to give you this. Can you make checklists so that you can go like, okay, if I'm writing a function, I think these pieces need to be in the function, regardless of what the function does, okay? So you can now write your own little checklist. It's like entry code, okay? What is important about the entry code? Exit code, what is important about the exit code? What should I check? Make a checklist, okay? When you need to access an item on the stack, okay, like a parameter or local variable, what do you need to do? What is the checklist? What are the things that you have to go through? Regardless of the sequence of instructions to get the job done, you have to ask yourself what needs to be done. So that's another checklist. Okay. When you are implementing a loop, like a for loop, you have to ask, okay, what are the things that must be in a while loop? You have a begin label, so you can go back to the beginning. You have an end label, so you can exit the loop. Right before the end label, you have an unconditional branch back to the begin label, so that it becomes a loop. And then you have the condition to get you out of the loop. So you need to, so that part is, it depends on what loop we're dealing with, the exit condition, but you need those major pieces. What about the if then else statement? You have a condition, you have a label marking the else branch, and then right before the else branch label, you need a JMPI to go around the entire else branch. Then you need an end branch for you need an end label for the entire conditional statement, so that the then branch, when it's all done, it can go straight to the end of the entire conditional statement. And then your condition should be negated, because you're looking for you're looking for the reason to go to the else branch. If you do not go to the else branch, then it continues execution with the then branch. That is the structure. Can you convert that description into a checklist? Because if you have checklist, then you don't have to keep everything in your head. You just go like, oh, what am I dealing with here? Oh, this is a conditional statement. You pull a blank checklist from your pile of paper, okay? And then you go like, okay, do I have this? Check. 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 Then you can use a highlighter in the exam paper and just go like, okay, these are all checked. Okay, because the way that if you do it this way, the way you process and verify the program is not going to be linear nor sequential, but you're doing it in a structured way, which also means, okay, you kind of need ways to kind of mark things that you have checked already, so you don't go back and double check those things. So I'm just trying to help you strategize, how to approach the final exam. Okay. Do we have any questions right now? Yeah, go ahead. Yep. 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 So it's still correct. Yep. I do not know. Haven't tried it yet. You are free to try it. That does not violate any rules that I have, because your actual final is going to be on paper, which means you can use the ChatGPT engine as a learning tool, okay, which is great. You can even ask ChatGPT what would be a good strategy to deal with questions like that. I'm not sure whether it will give you really good suggestions, okay. It might, it may not, but my personal suggestion is to use a checklist, because I know this stuff inside and out, but is it possible for me to forget one little thing? Absolutely. Okay. You know, so having a checklist means, okay, I just have to identify what I'm doing, and then I just have a checklist to, you know, very procedurally check off those items. Okay, which turns the whole thing into it's just more or less following a procedure kind of thing. You still need to understand the instructions really well, because I may not give you a typical sequence of getting something done, but it will still get the same stuff done. So you have to be so don't get too tied into the exact sequence of instructions that we talk about in class, and instead you ask, what does that sequence of instructions accomplish? Okay, but I may not give you the same sequence of instructions in the actual test. All right. So does that help you guys, kind of strategize a little bit? Okay. So I would test your strategy on this one, okay, because you have all the time in the world, okay, because there's no time crunch on this one. So now you can go like, okay, I'm going to try this approach. I'm going to try this strategy and see if I can come up with the answers. And I can share the answers of this particular test with you, and I can go through that, just going through mentally, what mistakes I have introduced into this particular program. But I want to leave you guys to do it first. Okay, I don't want to just give you the answer, because otherwise some people have really, really good memory and they go like, oh, I remember text said there's something wrong here. Okay, that defeats the whole purpose of giving you the test to begin with, because I want you guys to develop your own strategies to find out, okay, how do I check this code whether it's right or not? Okay, any questions? So the Chat GPT thing is all new this semester. Okay, I just got it done, what, 2 weeks ago or maybe a week ago. Um, you can test it out. I cannot make 100% claim that it's going to be correct all the time, but I think from what I have observed, it is actually quite capable. Um, so use it as a backup. Okay, if you need to talk to me in person, I'm always available during my office hour, and we don't really have scheduled lab activities anymore. So that what that means is, at the lab time of today, which probably begins a little earlier because we don't have anything else to talk about. You can either stay here and continue with the implementation of those two programs that are due. You can stay here and do that and ask me questions if you want to, or you can just kind of go like, okay, I think I do better, with no people around, and I just want to go to the library to do this. Okay, that's fine with me too. So it's going to be a flexible time, and you guys can. I'll stay here until the last student leaves, or 1:20 p.m., whichever one is earlier. Um, yeah. Any questions? Okay, well, since there are no questions, I'm gonna use up the next 10 minutes too, because I just like to talk. Well, that's actually not true, but I think some people can benefit from this discussion. The implementation of the Fibonacci program and also the Traverse program, you need to strategize how to implement and test and debug those programs. In other words, do it in small steps. Okay. Um, if you have not watched it, I am fairly sure that I made an announcement about that too. So let me just double check that. Because I made a video for my Tuesday, Thursday class about how to implement um, the, oh, maybe I have not done that. Okay. So since I have not done it, I'm just going to go to the YouTube channel and I'll point to you which one you might want to watch if you have not started yet. Okay. Or even if you have started, you might still want to watch it. Um, this one. So this one is from the 26th. It was intended for my Tuesday, Thursday class because I forgot to record on that day. You can watch this because this is a shorter one compared to the actual lecture in this class, but it does summarize, how you can kind of divide the Traverse program into multiple steps. And I will make sure that I share that file with you in this class. So let me go back to announcement and actually send that out. So I'm gonna add this one. I might have shared it already, but I just want to double check. So this is Traverse support files. See attached. I believe it is Traverse 4 as a zip file. Nope. Okay, I don't have that zip file. Okay, go ahead and create it. Yep, I just deleted it. That's all. So I need to zip traverse.zip, traverse star.c, traverse star.ttpasm, stash all of those, and then share. So now I should have traverse.zip. There we go. All right, so let me just kind of quickly go over all of those files. All right, the first one is traverse.c, which is the actual homework assignment. And it is a little bit difficult to understand and debug as it is. So traverse 0 is what I suggest people to do. It's simply to make sure that you can access the parameter pointer and go to and halt at the right instruction. In other words, if I pass a null pointer, you should end up here. If I pass a non-null pointer, you should end up here. That's all, okay? Just to make sure that you know how to access a parameter, check whether it is 0, implement a conditional statement that does not have an else branch. That's all, okay? Just get that part done. So that's traverse 0. And to test this program as it is, you will need to change between you have to alternate between these two lines, which basically you're passing a non-null to traverse, you're passing a null to traverse as pointer. Okay, so that's the first thing you need to do. Second, okay, so the second one is traverse 1.c. Okay, so this one, is assuming that you already verified that you know how to check whether pointer is null or not. Then you let's say go like, okay, I'm gonna forget about all the traverse, the recursive call, okay, because it's harder to debug recursive call. You might end up with an endless recursion, and then things are difficult to debug. Just implement these two, okay? So without the complication of recursion, without the complication of, oh, this whole thing may end up doing something indefinitely, just get these two things done, okay? How do I know whether my program is getting these done correctly or not? You can use the C code, okay? This program can be compiled. So you can now test this program with online GDB, VS Code, code blocks, whatever C development environment you want to use, but use that environment to find out what is happening. So I can tell you what you should be observing. You should observe how the first element of buffer is getting a value. You should observe also how local variable p of main is also getting changed. This statement on line 15 will change local variable p of main. This statement on line 14 will put a value into the first element of buffer, which is a local variable of main. Okay. Using a debugger in C, you can actually observe exactly how those two things are changed. Your assembly code should accomplish exactly the same thing. Now, would P be at the pointing to the same address? No, it's not going to point to the same address. Okay, the variables are all going to be at different locations. Okay, but it should still have the same effect of incrementing the value of P. So instead of pointing to the beginning of buffer, it should point to the second byte of buffer. That's what the effect is supposed to be. And then inside the buffer, the first element should be updated using the value member, the value of the member value of the structure that the pointer is pointing to. So now it depends on, are you passing n1 to it? Because if you pass n1, then the first element should have a value of 5. If you're passing n2, then the first element of buffer should be 3, and so on. So that's how you can test this program and debug your TTP ASM code. Because if you get this part done correctly, then you move on to the next one. So now you can go to traverse 2.c, which has only one side of the recursion. So instead of having a double recursion, it only has a single recursion, which is easier to debug because it doesn't backtrack and overwrite the stack. Okay, you can still see the trail of the stack because nothing is being overwritten in this process. So once again, you test this with the C code, find out what it is doing to P and buffer of main, and then you go to your assembly code and use the C code behavior to kind of double check against your assembly code implementation. If you can get this part done, okay, then the next one is just finish the whole program. Because if you can get this done, the next one, which is traverse 3.c, is to uncomment the second recursion. Because if you can get the first recursion done correctly, I really don't think there will be any problem getting the second recursion done also. So that would be kind of the easy step of the entire process. So I would break it up into these 4 stages, or five, four, five. I cannot remember. Okay, but either way, with each stage, you still want to also debug your code gradually. Use the halt instruction. Go like, okay, I just wanted to halt right here because I know right now this register or this memory location should be blah. Okay, just put a halt instruction. Okay, so this way you can focus on just that result. If that is not the result that you get, don't move forward. Keep debugging that part until it is done. All right. Are we okay so far with the strategy for the Traverse program? Okay. You can kind of interleave, between working on the Traverse program and the final exam because they really are about the same thing. You might read the final exam and learn about something. It's like, oh, so that's how we do blah blah. Okay. And then you can try that out in your program to see whether it works. Or you might work on your program for a while, and then you look at the final exam, go like, "Oh, I know what's wrong with this code, because my solution is right. I double check, I verify it, and the final exam is not using this code. It's missing this instruction here, or has an extra instruction here. So you can kind of you can interleave between implementation of Traverse and trying to work on the final exam. I think they are beneficial. Kind of they can cross pollinate a little bit. Um, all right. So I have just used up the extra 10 minutes, and now I can let you guys leave the class without feeling guilty that you guys pay for the money for 80-minute class and I only gave you less than 80 minutes. That would not be good. So you got your money's worth. The grades. What do you mean? You mean for the swap assignment? Give me some time, because it depends on how people turn in the grade, turn in the code. I have to test run every single one. Yep. Do you think you got it done? Okay. Yeah. Hmm? So the stack pointer get to zero, but did you see 07 becoming 03 and the 03 become a 07? Okay, and you use all the conventions, the caller call the agreement. Okay, well then it should be fine. Yeah. Question? Yep. Oh, okay. Don't make any changes. Let me look at the timestamps. Oh, okay. Mhm. Mhm. Oh, okay. Okay. So take a screenshot of the timestamp stuff, and then. Mhm. Is that the one that you want to turn in? Okay. All right. So I am just kind of quote unquote observe you doing this, and then send it as an attachment to me. Yeah, to my email. So turn in the screenshot and also the file. It's AUYEUNT at arc.losrios.edu. Yep. So just include the screenshot and also the file itself. Hmm. That should be fine. I can. No, you don't have to. I'm only providing the main so that people have something to test it with. Yep. Hmm. That's fine. Yep. Not a problem. All right. Sent. Okay. Thank you. Hmm. 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 Okay. Okay. Well, send me an email so that you can um, so that I can extract that file for this assignment, and then you can, because otherwise, if you turn in the homework for the one due on the 11th, it's going to overwrite this file. So send me an email that you made a mistake, but I should still be able to find the file, but in a different homework assignment. Yeah. Yep. Hmm. Hmm. That's fine. Yeah, that's fine. Yep. Hmm. So in your case, what I'll probably do is I'll just copy your entire swap function, paste it into your main. Huh? I will have to do it manually. Then I'll run it, because then I can check the actual locations FE and FF to see whether the 07 and the 03 were swapped. Yep. Hmm. But as long as your function works the way it's supposed to, it should not matter how main has everything set up. Yep. Hmm. Hmm. Uh-huh. Yep. Yep. ChatGPT. Hmm. I see. Oh, you didn't see the space. Uh, mm-hmm, mm-hmm. Okay, so it will still work, except it won't return to the correct location. It will return to location zero, which repeats the whole thing again. Okay, okay, alrighty. Uh-huh. Let me just turn off the recorder because it's still running. Not that there's anything top secret here, but I don't